All right, Chemistry 3111. This is where we left off last class. We were looking at question 16.13, and we covered question 16.13c, and now we're going to take a look at D, E, and F. And the question simply asks us, predict the products for each of the following reactions. So these are all 4+2 cycloadditions. Just to refresh your memory, what's a 4+2 cycloaddition? Well, we have what's called a diene that has 4 atoms that are involved in the reaction, right? We have 1, 2, 3, 4. And again, a diene could have more atoms than 4, or more carbons than 4, let's say. But these are the 4 atoms that are involved in the cycloaddition. And then in our dienophile, we have 2 atoms that are involved in the cycloaddition, right? We have 1 and 2 here like this. Now, in terms of determining what the product is going to look like, I think it's always handy to draw the curved arrows for a 4+2 cycloaddition. Remember, we went over this last class. We said if we have a generic, diene like this and a dienophile like that, and we're adding them together, that you can draw the curved arrows like this, and that would be a clockwise fashion, or you could draw them in a counterclockwise fashion. Either way, you're going to end up with the exact same product, right? If you draw the product, you end up with something that looks like this. So you've ended up eliminating 2 pi bonds, right? Overall, you had 1, 2, 3 pi bonds when you started out. You've only got 1 here, so you destroyed 2 pi bonds. In the starting material, you only had 1, 2, 3, 4 sigma bonds, but you have 6 sigma bonds in your final product, and so you've created 2 sigma bonds. So you lost 2 pi bonds and you created 2 sigma bonds, and since sigma bonds are stronger than pi bonds, that's why this is an exothermic reaction. Anyhow, with that in mind, we'll get rid of that, and we'll try drawing those curved arrows with our diene and dienophile, right? This is 1,3-butadiene. This is our diene, and this is our dienophile. And you might remember that what we talked about last class is that the dienophile, in order for it to be reactive, it's got to have electron withdrawing groups. And you can see that we've got a carbonyl here on each end of the dienophile. And so we do have electron withdrawing groups because the carbonyl is a polar bond. So let's draw some curved arrows. And again, you could draw them clockwise like this, okay? Or you could draw them counterclockwise. Now let's think about this very carefully in terms of what the final product would look like. We know that we're forming a 6-membered ring. So you could just start with this, 1, 2, 3, 4, 5, 6, like this. You can see that we're forming a pi bond right here. So we can put that pi bond in here. And you also see that in your dienophile, you only ended up using 1 pi bond to do the reaction, and you still have a pi bond here that remains intact. Well, remember that if you have a double bond on each of these carbons, that they're sp2 hybridized, and so their molecular geometries will be trigonal planar. So when we draw the bond to the carbonyl, okay, and I'll draw it like this, okay? When we draw the bond to the carbonyl, we don't have to worry about drawing dashes or wedges because, again, each of these carbons is trigonal planar. And so that is our product right there. So we end up with a molecule that is an analog of 1,4-cyclohexadiene. So I didn't mean to do that. There we go. So this is an analog of this molecule. Oops, where's my red pen? It's nice to know how to name a few of these molecules. So if you have 1, 2, 3, 4, 5, 6, this is called 1,4-cyclohexadiene. Okay, so that's an analog of 1,4-cyclohexadiene. All right, let's take a look at the next one. We have the same old diene, which is 1,3-butadiene. This molecule here is called maleic anhydride, and I'm not going to go into the details on that, but maleic anhydride is a molecule that comes up every once in a while in organic chemistry. Well, now we're doing a reaction between the same diene, but now our dienophile doesn't have a triple bond, it's only got a double bond, right? And if you notice that on that double bond, not only do we have the 2 bonds to the carbonyls that are here, but we also have 2 hydrogens here. And so the double bond is essentially, or it is, a cis double bond, right? Both of the hydrogens are on the same side, and both of these groups are on the same side. So this is a cis double bond. And you remember that when we have a cis alkene, that we're going to end up with these two groups, this group and this group will be cis to each other in our final product. If you don't remember what I mean, let's draw some curved arrows. So let's get the red pen out here. And we're going to start, and we could do counterclockwise this time just for fun. We'll put one here, one like this, and then we'll put our curved arrow here like that. So let's draw what the final product would look like. We're going to have a 6-membered ring because we have a total of 6 atoms involved in the transition state. We have a pi bond here, and then we're going to have 2 bonds, one going up like this and one going up like this, okay? And that's these 2 bonds right here, right? They're going to be cis to each other. And then we have our carbonyl like this, and then we have our oxygen like that. Now, I could have drawn those bonds that I have drawn as wedges. I could have drawn them as dashes. It doesn't matter. Okay, I could draw them as a dash like this, and it's still the same molecule. Could anybody tell me why this is the same molecule as if I drew it with wedges, like I had a few seconds ago and I erased them? Why is this the same molecule? How do I know that? There's something special about this molecule in terms of its chirality or its chiral centers and the relationship to each other. Does anybody remember the term meso? All right, we have a compound that has 2 chiral centers. I have one here and I have one here. However, there is a plane of symmetry running through the compound, and so this is a meso compound. So whether I drew it up or down, it doesn't matter because there's a plane of symmetry running through the molecule. It is a meso molecule. Give me a thumbs up if you follow me on the concept of meso. Do you remember that? Or if you're like, well, I didn't remember it, but maybe I jogged your memory a little bit. All right, good, excellent. All right, well, let's keep moving and let's take a look at the next one. The next one is kind of similar to the first one that we looked at today because our diene is 1,3-butadiene, and our dienophile, this time it's not an alkene, it's an alkyne, right? So we're going to make some kind of analog of 1,4-cyclohexadiene. Let's draw our curved arrows. I'll use the green pen this time. So we have something that looks like this, and like that. Draw the product arrow, and we're going to end up with a 6-membered ring that's going to have a double bond here and here. Again, remember that since both of these carbons are sp2 hybridized, I don't have to draw dashes or wedges off of them. That would be incorrect. And I put my 2 nitriles out there like that. Remember that a nitrile, a CN, is an electron withdrawing group. I mentioned that to you last class, that a nitrile is an electron withdrawing group. All right, so there you go. So that's a little practice in some Diels-Alder, and we're not done with the Diels-Alder today. We're going to look at some other problems that involve Diels-Alder. Like question 16.16, the question gives you 3 different dienes, and it asks you to rank them in terms of their Diels-Alder reactivity. I'm going to call this one A, this one B, and this one C. Could anybody tell me which one of these would be unreactive? The totally least reactive, just nothing's going to happen. There is one of them that is totally unreactive. Could anybody tell me which one would just not do anything if you put it in the presence of a dienophile, right? Because they're all dienes. We have a diene here, we have another diene here, and we have a diene here. But there's one of them that's special in that it will not react, okay? Now, if you remember that when we have a Diels-Alder reaction, our diene has to be in the S-cis conformation, right, in order to react, okay, with the dienophile. So the problem with A is that the diene is locked in the S-trans conformation, right? So if I delete this, right? So if I draw S-cis, which looks like this is S-cis, S-trans looks like this. So S trans. And you can see that this diene is locked in the S trans because it's in that bicyclic system. So unreactive, since locked in S trans conformation. All right. Now, if I look at the other two, what's interesting about B is that it's going to be the most reactive. Why would that be? Because if you look at the diene here, it's locked in the bicyclic system. So most reactive, because locked in S cis conformation. So that one is going to be the most reactive. The other one is going to be intermediate in terms of its reactivity, right? We can rotate this carbon-carbon sigma bond so that we have the diene in this conformation, so that we have it in an S-cis conformation. However, it's going to look like this. And because you've got a methyl group here, right, you've got another methyl group here, and of course you have them here too. But because you've got those big old methyl groups, there's going to be a little bit of steric hindrance there. And so even though this will react, of course it is going to react with a diene, or sorry, a dienophile, but it's not locked in the S-cis conformation, right? And there's going to be some steric hindrance here as well. All right. So that's how you would differentiate between those three dienophiles. So remember, when you have your diene locked in the S-cis conformation, it's going to be the most reactive. If you have it locked in an S-trans, it's going to be unreactive. All right. And then if you have it in an S-trans conformation, which it is right here, but you can rotate it to put it in an S-cis conformation, well, in that case, it's going to be intermediate. Okay, let's move on from there, and let's try question 16.17, which is still about Diels-Alder chemistry. It's kind of the major focus of this chapter, except now we're starting with dienophiles that are cyclic, right? This is a dienophile, but now you have a cyclic dienophile, and when you have a cyclic dienophile, diene, jeepers, Mr. Dion, I need more coffee, I think. There we go. When we have a cyclic diene, we're going to form a bicyclic compound, right? We're going to end up with some kind of bicyclic compound. Now, the first thing we're going to do is draw the curved arrows. So we'll draw a reaction arrow like this. So here's our diene. This is our dienophile. And remember that since the diene is symmetrical, we don't have to worry about regioselectivity in terms of which way do they align, right? There's a plane of symmetry right down here through the diene. So we don't have to worry about flipping this around or anything like that. We will look at problems today that involve regiochemistry. However, this isn't one of them. So let's draw the curved arrows carefully. We start by breaking this pi bond. We're going to have a connection between this carbon, that's why I dragged the arrow through it, to this carbon. We're going to break this pi bond. We're going to form a bond through that carbon over to this carbon here. And then we break this pi bond, and we're going to make a new pi bond there. So we're forming two sigma bonds, and we're breaking two pi bonds, and we're making a new pi bond at the same time. So let's draw what we'd end up with. All right, if you were just learning this, you might think, okay, well, I've got my 5-membered ring like this, right? And then I've got a bond going down here and down here. And don't draw it this way. This is totally wrong. But, you know, if you're really struggling, you might draw it something like that, okay? But there's a much better way to draw it, and I'll show you how to do that. So you start by drawing this piece here, these 4 carbons, and you would draw them like this, 1, 2, 3, 4. Okay, and we can make this even a little longer like that. Then you draw the bridge, okay, the small bridge, and it's going to go way up like that. So that's your 5-membered ring, okay? That's got the double bond here. So basically all I've done is I've covered these 5 carbons, 1, 2, 3, 4, 5. There you go. All right. Now, the 2 new bonds that I formed, okay, I formed 2 new bonds here and here, okay, with my green, highlighter and pointing out those. So those are going to look like this. I'm going to have one going down like this and one going down like that. And then the two carbons in the dienophile are here. Okay. And then I've got my aldehyde. Now there's two positions at this carbon, right? I either have a position going up like this and I have another position going down like that because it is tetrahedral. However, this position here, this is the exo position and this is the endo position. And you remember the endo rule that the dienophile is going to align itself in such a way with the diene that it seeks to form this or to have this favorable interaction between the pi bond here or the orbitals here and the orbitals involved in the new pi bond that's being formed. And so the endo is going to be the major product. So let's draw that. So let me erase some of this spinach here. And we're going to have our aldehyde pointing down. So we have our aldehyde. I'll draw the condensed structure, CHO. And then we can draw the proton going up like that. So not only are we going to have that, but we're also going to have the non-superimposable mirror image, right? Because this is a chiral center, okay? Don't believe me? Look, you've got a hydrogen here. You've got the aldehyde here. Look at this carbon. This is a bridgehead carbon with one hydrogen, and this is a CH2. So obviously, that is a chiral center, the one that I have the star on. And so we could form this compound, and we could also form its enantiomer. Oops. There we go. So you can either write plus enantiomer, or you could try to draw the enantiomer, which is just the mirror image. Okay, but I'll just write down here plus enantiomer like that. All right, there we go. Let's move on to the next one. Again, we have our diene that's locked in the S-cis conformation here in this 5-membered ring. Okay. We have our dienophile. It's trans, right? We didn't have to consider trans or cis up in this one because it didn't exist. But now it's trans, so that means when we form our new ring, one of these is going to be going up and the other one is going to be going down, right? So when we form our bicyclic species, let's start by drawing some curved arrows that show the flow of electrons in the Diels-Alder reaction. So we'll start with the new bond being formed here, this bond being broken, and the new bond being formed here, and then the pi bond being formed over here. So we'll start with the 5-membered ring, right? So I'm going to start by drawing this part. So that's going to look like this. So I draw 1, 2, 3, 4, and then I put 5 up here like that. I can do a little better than that. So let's do something that looks like this. And we'll put the sulfur up there like that. So there's my sulfur. I've got my double bond here. These two carbons are still sp2 hybridized. So I have my methoxy group here like that. And then I formed 2 new bonds like this. Okay. So again, if these two groups are trans to each other, these two carboxyl groups, right, one of them is going to be pointing up like this. So one of them is going to be in an endo or an exo position, and the other one is going to be pointing down in the endo position. Like, oops, let me clean that up a little bit. Come on, there we go. Like that. And to clarify, you can put the proton pointing up and the proton pointing down like this. And of course, you can also have the reaction occur to form the enantiomer, right? Because these are chiral centers. So we can end up forming this compound plus the enantiomer. All right, if you don't believe me that this is a chiral center, for example, that this one here is a chiral center, look, we've got a hydrogen here, we've got a carboxyl group here, we've got a bridgehead carbon here, and then we've got something completely different here. So that is obviously a chiral center. And this one is a chiral center for the same reason. Okay, this is not a meso compound. You can see that this is pointing down, this is pointing up, so there's no plane of symmetry in the molecule. So we have 2 chiral centers, and we could also form the non-superimposable mirror image, the enantiomer. And I can put my lone pairs and my sulfur up there like that. Now, if you look at the solutions manual, their bicyclic is going to be drawn a little prettier than mine, but either way, we get the point across there. Let's take a look at the next one. So we have our diene locked in an S-cis conformation. We have an electron withdrawing group on our Diene file. There's no cis or trans to even worry about here. Let's just try going a little faster here and drawing some curved arrows. We'll go backwards this time. Again, it doesn't matter if you go clockwise or counterclockwise like that. And we're going to end up with a 5-membered ring like this, okay, like that. We have these 2 methyl groups coming off the back. We have our new pi bond. We formed these 2 sigma bonds. And this cyano group, since I only have 1 group and it's the electron withdrawing group, remember that that is going to follow the endo rule and it's going to be pointing down. So it's going to be pointing down like this, okay? And we end up with a chiral center, so we'll also end up with the enantiomer like that. So we end up with the endo product, right? Remember, this is the endo position, right? When we only have 1 substituent, we're going to form the endo product, right? En stands for enantiomer, not endo. So this is endo. And then in this case, since it's trans, you end up with one of them being exo and one of them being endo, like that. All right, let's try another one. This one here is the reaction between this diene, which is locked in the S-cis conformation, and this dienephile here, which is also cis, and I talked about this earlier today. This is called maleic anhydride. You see the 2 hydrogens are on the same side, so these 2 groups, or these 2 carbonyls, are on the same side, so it's cis. When we draw curved arrows, so we start with this one here, break that one, form a new sigma, and we put a new pi bond here, like that. Let's start by drawing the 5-membered ring. So it's going to look something like this. So we have this. We have the oxygen in the top like that. We have this new pi bond here. We formed 2 new sigma bonds like this. Now, since both of the hydrogens are on the same side of the double bond and both of these groups are on the same side of the double bond, you're like, well, of course they're on the same side, Mr. Dion. It's a ring. Yeah, I get it. It's just the way of describing it to you. Well, both of the hydrogens are going to be in the exo position, and therefore both of the bonds going down, and I'm going to draw it behind like this, are going to be pointing down like this to form the ring. Okay, so it's going to look something like that. Now I'm going to clean it up by eliminating the hydrogens. Just bear with me. Where's my object eraser? There we go. So if I try to make it a little prettier, and again, if you look at the textbook, it's even prettier than what I draw. So there you go. It's going to look something like this, where we have our 5-membered ring, and everything is pointing down like this. And if you want to point out that the hydrogens are pointing up like this, no problem, right? So again, since this whole group here is syn to the larger bridge, this is the endo product. Endo product. I have a question for you guys. Will I also form the enantiomer in this case? Yes or no? Would I form the enantiomer in this case? So would I form an enantiomer here? Anybody make a suggestion as to yes or no in terms of enantiomers being formed? Yeah, exactly. The answer is no. Right? Why wouldn't I get an enantiomer in this case? I know you know. Right? I see my students say nah. Right? There's no enantiomer. Why? Tell me. Give me a 1-word answer. Like a game show. Give me a 1-word answer as to why. I'll give you a clue. Starts with the letter M. Ends with ezo. That's right, Jisoo. That's right. It's a meso compound, isn't it? This is a meso compound. Okay? It's not abundantly clear when you look at it this way, but you can imagine that if you were looking at it, I'll draw an eyeball the best I can. If your eyeball was looking at the molecule, kind of this way, you'd be able to see that there is a plane of symmetry in the molecule. You could even look at it just from the starting materials, right? You see that there's a plane of symmetry here and there's a plane of symmetry here. So there's going to be a plane of symmetry through the whole dang thing. I mean, the reason these two aren't meso is because there's no plane of symmetry here. There's an axis of rotational symmetry, but not a plane of symmetry. And then there's no plane of symmetry here. So just kind of food for thought there. All right, let's turn up the heat a little bit. This is like the old analogy of the frog in boiling water. And let's try question 16.8. This is where they get a little bit more interesting, because not only do we have to predict the product of a Diels-Alder reaction, but we have to consider regiochemistry, right? How is the diene and the dienophile, how are they going to align? Like, for example, in this problem here, are they going to align exactly the way that they're written? Or will I have to say flip my dienophile around like this, right? Is it this or this, right, in terms of my dienophile? So what do we do? All right, what we're going to want to do is we're going to want to draw some resonance contributors and figure out where the partial positive and partial negative charges are. Now, if you're a really quick student, and I'm sure that a lot of you are, you might be able to do these really, really fast and just say, well, just by inspection, I think that there's a delta plus here, and I think that there's a delta minus here, so I think that they're perfectly aligned. And there's nothing wrong with that if you're really quick at it. However, if you need to draw out the whole structure, and let me show you how. If you need to draw this out, for example, so here's my aldehyde, and say, well, I know that I could have a resonance contributor here like this, which is going to give me something that looks like this. This is called an enolate. Anyhow, there we go. And then I'd have a positive charge here. Right, so that tells me that there's a partial positive charge here. And then if you need to do this, if you need to say, well, I have two lone pairs here, so I could push some arrows like this, and then like this, or maybe I could fix that last one, like this, so that I end up with something that looks like this. So I have this, I have negative charge here, and then I have my oxonium up here, right? So then that tells you that you've got a partial, oops, where's my blue pen? Pardon me. Where is it? Hold blue. Here we go. So you've got a partial negative charge here just by, by drawing these structures, right? You've got the negative here and the positive here, so that tells you should have partial negative and partial positive here, which tells you that these are aligned correctly in terms of their regioselectivity. So then when it comes time to draw the reaction, and I'll just redraw everything here, there's enough room, okay, it means that your diene is going to align with the dienophile like this. Now you can draw your curved arrows, oops, for your Diels-Alder like that, and you're going to end up with something that looks like this. You're going to have a 6-membered ring, right? Because there's no, your diene is not cyclic, so you only end up with one ring. You've got a double bond here, okay? You've got your ether up here, just put OCH3. I like that. Actually, I don't like it. I don't like it when you draw them like that. I like to show the carbon being connected like this. And then you have your aldehyde, your CHO up here. Now, if you're wondering, if you're really astute, and I know you all are, you're like, well, hold the phone, Mr. Dion. This is a stereocenter, and this is a stereocenter. Are these dashes or white just not covered in our textbook? Okay, so don't worry about that. In this case, there's no endo rule to worry about here because we're not forming a bicyclic compound. So this is just about regioselectivity. Okay, when we look at regioselectivity, we will look at an example where you have to, we don't look at any examples where you have to apply the endo rule, or at least there's none that I had picked out. So let's move on to the next one. Let me draw it out here for you. So the next one, let me find it in my book. 16.8. I had it here just a second ago. So this is 16.18. Which one is it? I had it written down. Yeah, it's 16.18b. So this is 16.18. Oops, 18b. All right, so our diene has an ether on it, like this, and then our dienophile has a nitrile on it, like that. Well, for the diene, I mean, it's pretty quick to draw the curved arrows for that to show that the partial negative charge is going to be right here, okay? So we form this double bond, and we have our methyl group here. And then we have this pi bond here. So that shows us that you have a delta negative here, okay? But in terms of this guy, I think it would be, a good idea for us to draw the whole Lewis structure. Well, let's draw the Lewis structure of the nitrile, okay? Remember, and I've told you this before, but it bears repeating, that when you have a C triple bond N on an R group, that's called a nitrile. Okay, when you have Cn minus, right, which is this, okay, that's a polyatomic ion called cyanide. Okay, so cyanide is an ion. A nitrile is just a functional group in organic chemistry. So can we push some arrows for that? Sure we can, right? We could, oops, where's my red pen? There we go. All right, so we could push some arrows like this, and then we get a resonance structure, a resonance contributor that looks like this. So we've got a double bond here on our carbon, so now it's like an allene. We've got this, and we've got this. So that tells us that you have partial positive charge down here, right? Again, how do I know that? Because I've got negative charge here, so partial negative there. I've got a positive charge here, so partial positive there. What does that tell us? It tells us that it was lined up correctly the first time. So now I'm just going to rewrite everything. So I'll start by drawing my diene like this. You're like, of course I'm diene. This is organic chemistry on a Friday. And then we put our nitrile like this. We put in our curved arrows. So like this and this and this. And let's figure out what the product is going to look like. So we're going to have a 6-membered ring. We've got a pi bond here, so that means that this carbon is sp2 hybridized. It's trigonal planar. We don't have to worry about anything to do with stereochemistry there. And then we've got our nitrile over here. And if you're wondering, isn't that a stereocenter, right? Isn't this a stereocenter, Mr. Dion? It is. And we don't have to worry about, drawing it as a dash or a wedge. It's totally fine the way it is. We'll just leave it like that. Okay, let's try 16.18C. 16.18, and this is C. Let's draw it out. I like doing these ones where you have to think about the regiochemistry. And again, I know that some of you are probably able to solve these very quickly, and you don't need to draw the resonance contributors, but I recommend it. I don't think it's a bad idea. So there's our diene. All right, and here's our dienephile. This time it's an alkyne and it's got an ester on it. So here we go. Let's start by drawing the curved arrows for the diene like this. So we have a curved arrow that goes like this, and then another one like that. And when we draw this resonance contributor, we end up with something that looks like this. We have a negative charge over here, and we have a positive charge here, and we have our ethyl group. And so that tells you that this carbon is delta negative. Let's draw our ester so that we can actually draw a proper Lewis structure so that we can draw a proper curved arrow. So let's see, we can push these electrons up here and these ones up here, which would give us this resonance contributor where we've got a double bond. Maybe I need more room, like this. We've got another double bond here and a single bond to our oxygen, which is going to have a negative charge on it like this. We've got a positive charge down here, and we have our ester like that. So that tells you that this carbon is going to be partially positive like that. Again, how did I know? Because when I drew the resonance contributor here, I saw the negative charges here. That means that this is partially negative. When I drew this resonance contributor here, I saw a positive charge here, which means that this is partially positive. So that means I have to turn this one around. I mean, you could flip either one. It doesn't matter. It's neither here nor there. But I'm going to draw the dienephile, or sort of the diene, the same way it was from the get-go. So I'll draw it like this with my ethoxy group up here. And I'm going to flip my dienephile around. Comme ça, as we say in French. There we go, like that. Now I can draw some curved arrows to show the reaction mechanism. Use green pen. 1, 2, 3 curved arrows are always used for our cycloaddition reaction, our 4+2 cycloaddition, which is what our Diels-Alder reaction is. So now we've got a bicyclic compound. However, if you remember from earlier today, when we have a triple bond in our Diene file, we don't have to worry about the endo rule. But let's end up drawing, or let's draw. First, we've got a 5-membered ring that's got an oxygen in the bridge up here. We have a double bond here. We have our ethoxy group over here. We formed 2 new sigma bonds like this. We still have a double bond here. And we have an sp2 hybridized carbon here. So again, we don't have to worry about the endo rule. And we have our ester over here like that. And so that would be our final product. Give me a thumbs up if you follow me. If you're like, you know, Mr. Dion, that helps a little bit. I hope it helps you a little bit. I don't think any of these questions are easy, but I think they're very good problems in terms of, you know, working on our Diels-Alder prowess. All right. Well, if you think about every one of these reactions that we looked at, say just this reaction right here, you know, could you draw, if I erase the curved arrows for the reaction, and if I erase this arrow, you don't have to do this, but could you draw the arrows going backwards? Right? And if you're like, well, shouldn't it just be the same 3 arrows just in reverse? Yeah. So you'd end up putting an arrow here, an arrow here, and an arrow here, and that would take you right back to these 2. Okay? That's the curved arrows for the retro Diels-Alder. And what we're going to look at next, let me show you, is another question from the textbook, which is down here. And it's where we start with the product of a Diels-Alder reaction like this. And it asks us to draw the reagents. So now we have to flip it around. So this is why it's imperative that you know how to draw the curved arrows, in my opinion. Okay, like let's take a look at A. We've got a 6-membered ring with a double bond in it, right? If we start by drawing the curved arrows in reverse, you could always start on the pi bond. I find that helps students if they start here. You can either go this way or you can go this way. So then we end up with 3 arrows like this, right? It's a cyclic reaction. It's a concerted mechanism. What does concerted mean? That would be a good question for your quiz. Concerted just means it all happens together, right? It all happens at the exact same time. So if you draw what you would get, you know, after you drew those arrows, look, you end up breaking, right? You're breaking this bond and you're breaking this bond. So that means that your diene is going to have 1, 2, 3, 4. You've got a double bond here and a double bond here, but you've got these 2 methyl groups on it. You've got a double bond here, or sorry, a methyl there and a methyl here. So what you have is 2,3 dimethyl 1,3-butadiene as your diene. And your I'm going to ask you guys a question. Will my dienophile be a cis or trans alkene? And it's not a trick question. Right, I'm making an alkene because I'm making a double bond right here. Oops, I wanted the green highlighter. But I'm making a double bond right here. Will it be cis or trans, my alkene? Yes, thanks, Gilbert. Absolutely. How did he know? And Courtney, like, how did you guys know so quickly that it was going to be cis? Right, because these 2 groups are cis. Therefore, you're going to end up with a cis alkene. Alkene. Okay, right. And if the 2 groups are trans, you'd end up with a trans alkene. All right, well, let's draw what this cis alkene is going to look like then. All it's going to have is 2 bonds like this in our dienophile, and then the 2 carboxyl groups are going to be cis to each other. So we draw a carboxyl group here and a carboxyl group there. And that's it, my friends. Nothing more than that. Give me a thumbs up if you think you could do that one, or stop me if you have a question. I just want to make sure that you could draw, or at least you feel like you could draw those curved arrows before we move on to the next one, because I think it's a little more complicated when you have a bicyclic. Great. I'm digging that. The thumbs up and a smiley face together. It's a good day. All right. Let's try the next thing. Never be intimidated by these kinds of problems, okay? Just take it one step at a time. Look, we've got our pi bond right here. I've found, teaching this class, that the easiest way for my students to start is to start with the pi bond and say, okay, well, the pi bond's going to move over here, right? I'm putting it in between these two carbons, right? It might not look perfect because you've got this bond in the way, but that's where it's ending up, okay? I'm going to break this sigma bond. It's obliterated. I'm going to make a pi bond here, and then I'm going to break this sigma bond. Now, I could draw it inside the ring, but you see how it just makes it look like crap, pardon my language. So I'm just going to draw it like this. So there you go. So that means I've got a 6-membered ring. Look, 1, 2, 3, 4, 5, 6. Okay, so I form a 6-membered ring with 2 bonds. Two double bonds is what I should have said. So that means I'm going to end up with a 6-membered ring. Let's draw it like this. 1, 2, 3, 4, 5, 6. And I'm going to have a double bond here and a double bond here. What's that? That's 1,3 cyclohexadiene. Now, in terms of my dienophile, right, I'm going to have a double bond, and it's going to have 4 nitrile groups attached to it. So you end up with tetracyano. It's called tetracyanoethylene. Does that get some serious electron withdrawing groups on it, or what? Okay, sound like Bob Ross, right? The liquid white. Anyhow, but I got a lot of electron withdrawing groups on there, so that thing is really hungry to react. Okay, now obviously these are not reactions. I mean, I just keep treating them like they're reactions, which maybe I shouldn't be doing. Really, what I should correctly be doing here is erasing these and drawing retrosynthesis arrows, shouldn't I? Right? Because it's just asking me to, to tell me or asking you to tell what the starting materials would be. Right? If it was to go backward, that would be a real retro Diels-Alder reaction, and you should understand what causes a retro Diels-Alder. We looked at Gibbs free energy and how it relates to Diels-Alder and retro Diels-Alder, and when you increase the temperature, it increases the entropy term, and so it causes the reaction or the delta G to be positive, and so it forces the retro Diels-Alder. All right, if you could do this one, I feel like if you could do both of these, and I don't like to make blanket statements as an instructor. I think that's, something that's fraught. But I would think that if you understood the curved arrows in these first two and were able to come up with these, that the next two wouldn't be too much of a stretch. I would think that you'd be pretty quick at it. Let's try the next one, and let's do it a little quicker this time. Look, we've got our double bond over here. Let's draw some curved arrows, my friend. So we're going to form a new pi bond here. We're going to break this sigma bond, form a new double bond. We're going to break this sigma bond, and so we're going to end up with one of our starting materials being a 5-membered ring, and it's going to have 2 double bonds in it like that. Look familiar? This is called cyclopentadiene. So in case you didn't know, we talked about it the other day. So cyclopentadiene. I told you when I introduced you to the name of this compound, what I said is, since it's locked in the S-cis conformation, if it sees another molecule of cyclopentadiene, it will just react. Okay, and I said, well, you have to jack up the temperature and heat it up because you can't store it for a long time. So what is our dienophile going to look like? Could anybody tell me, would our dienophile, would it be cis or trans? And it's not a trick question. I'll just throw that out there to my students. Would my dienophile be cis or trans, do you guys think? Yeah, absolutely. Absolutely, right. How did you know that? Because both of these aldehyde groups are on the exact same side. Yes, yes. Okay, so I'm going to have double bond like this. I've got my aldehyde over here and an aldehyde here. And there you go, my friends. Those are the starting materials that you would need. Let's try the last one. Okay, let's give it the old college try. Let's do this one for Clyde, our school's mascot. Curved arrow here, here, here. If there's one thing you should get out of this chapter, it's how to draw the mechanism for the Diels-Alder, right? You have to draw it, seemingly Avogadro's number of times. So what do we end up with? We're going to end up with a 5-membered ring that's got an oxygen in it, 2 double bonds like this, and then we end up with this guy that we've seen several times today. I think this is the 3rd time this molecule has shown up. This is called, again, maleic anhydride. And if you want to Google maleic hydride, you could even look up an article about it on Wikipedia and learn something about maleic anhydride. Is it always safe Is it always safe to say that? Yeah, I see what you're getting at, Gilbert, from your question. Yeah, I would say yes. Yes. So so what he's saying is that whenever you have a bridge here that's got one carbon or one atom, you always end up with a five-membered diene. And he says whenever your bridge has two carbons, then you always end up with a six-membered ring as your diene. Yeah, I'd say so most of the time. I don't want to make a blanket statement, but I can't think of an exception right now. Okay, sound good? But you know what that shows? This shows that you're looking for patterns, which is a good thing. I think it's always a good thing to look for patterns in organic chemistry because that's what science is, right? Looking for patterns and looking at the data and seeing if you can draw a pattern that you could use. If there's one thing I've learned teaching science classes, and this isn't a comment about any one student, this is a comment about virtually all of the students I've ever taught, is that science students, what they have in common, we all come from, diverse backgrounds, and which is a beautiful thing. But then when you talk to students, science students are like kind of like this. They're like, Mr. Dion, give me the rules. Tell me what the rules are, and I will follow those rules, and I will get a good grade when I follow those rules. And I think that's exactly how science works. In a science class, like organic chemistry, you want to learn the rules, you want to know them well, and you want to follow them.